Hello, my name is Henning Tiemeier, and thank you for tuning in or listening to this session, this educational session. It's number 2 of a series of educational sessions on population neuroscience, essentially epidemiology meets neuroscience. And I would like to take the time, or your time, or if you bear with me, to talk about 7 problems, which I've termed 7 plagues of conventional brain imaging studies. And that's meant to pave the way towards population neuroscience. Let me just tell you a bit about conflict of interest. It is because this talk, although it's very broad, it will talk about biases and epidemiological challenges. The examples I use are largely from neurodevelopmental imaging studies. And that's because I have worked with these both in the ABCD study and the Generation R2 of the largest worldwide neuroimaging studies, which are population-based. What are the learning objectives? What do I want you to understand? I want you to understand the epidemiological concepts in the context of brain imaging. So not an epidemiological lecture, it's really in the context of brain imaging. And what the skill I was going to try to teach everybody who's listening is to become aware of these epidemiological challenges, both in his own work and when you read neuroscience literature. And there will be a bit of time to go into some suggestions for possible solutions of these challenges. I want to start introducing the problem by giving an example from what I call the dark age. And this dark age pertains to the candidate gene study. It should say candidate gene study. And I'll use my own work or the work of my colleague, Sandra Lopez-Leon, as an example. When I was a postdoc, so many years ago, I must tell you, and that continued for many years, she worked on reviewing all the candidate gene studies of major depression. And that was a frustrating work because essentially every day she worked, there was a new study appearing, always candidate gene studies in relation to depression. Now, the sad part of that story is that about 10, and the work continued for 10 years, so it's nearly 20 years, if you wish, later, all the work is essentially for nothing. If you believe the reviews and the studies of nowadays, then all of these studies don't replicate, or the review findings at that time don't replicate. Essentially, it says, at that time, those candidate gene studies were wrong. But what does it have to do with neuroimaging? I think it has a lot to do with the current day neuroimaging, because I think much of our studies don't replicate. If we continue like that, I think there are epidemiological biases. And it's not, as this review points out, in the case of genetics, not phenotypic measures. We won't overcome it with better MRI measures, better neuroscience, if you wish. We'll have to do epidemiology. That is the lesson that we must learn and take from these dark ages of genetics, because arguably geneticists have learned it and are today adhering to epidemiological principles. Okay, so here's essentially the overview of what I would like to talk about. I termed it 7 plagues. I have to restrict it to 7 problems, and here you can read them. Confounding, the problem of directionality, or no life course or timing in our models, the testing, the multiple testing, I mean, that there's little specificity and small sample size, and no representative studies, if you wish. I'll come into that. And I'll illustrate it with some slides, with some pictures, essentially historical old pictures of the 7 plagues. Here's the first etch, if you wish, and that is confounding and extraneous variables. And there you see the extraneous factor falling down on Earth in this very old painting. My first example from neuroimaging studies pertains to autism imaging. And here is a wonderful review, and a review that focuses on one thing, namely the IQ of the cases with autism and the controls. Take a look at it for 1 minute. You see the ages, you see the gender ratio, but you can also see the IQ, both of the cases and the controls. If you quickly skim the IQ, you will see that it is lower than the controls. So far, so good. But you will also see that many studies have autistic cases with quite high IQ. If you know that in the general population, the IQ of children with autism is often, or on average, below 70, is very low, then it is remarkable that in these imaging studies, the IQ of the cases is much, much higher. What is also remarkable is that the IQ of the controls is not around 100, but it is, as you can see, on average, or nearly always above 100, and the average is clearly above 100. So what I'm trying to point out is that the controls are not representative of the general population, are not typically sampled from the general population, and neither are the autistic people sampled from the typical population. What does that mean? Well, it will introduce, probably, even if we pull all these studies together, some bias. It will introduce confounding by selection bias, probably, it will confounding or selection bias, however, if you wish to term it. But it is important that these studies will likely not be, if you wish, valid and tell us much about the differences, because both the controls and the cases are not well sampled. I'll give you another example, and that will stick to autism, is another more recent imaging study. Now it's a big imaging study. Enigma is a consortium that pools autistic cases from many, many different sites and then studies them collectively. And what is interesting is that in this study published in the American Journal of Psychiatry just 2 years ago, they controlled for only 2 confounders, sex and IQ. And actually, if you wish, strictly speaking, sight, because it comes from different sites. But they only corrected for the IQ, so that's good that they did that in a way perhaps better than the studies I just showed, and they controlled for sex. However, there are arguably much more factors that are relevant for autism and that differ between the cases and controls. And you could argue it's parental SAS, it's the race, it's whether you're on medication, it could be the birth weight, it could be many factors that differ between cases and controls. And so I want to make you aware of that many of the imaging studies nowadays are not well controlled. And does that matter? Why does it matter? What could it mean for our results? I'll show you on the next slides. But first, bear with me for another moment and think of other factors, even other situations. If we don't, let's look at autism, in situations when we image children who have undergone abuse, then the list of confounders is really endless and include much more, well, much different factors, so family status or maternal health indicators. But let's stick with our example of confounding and the brain and look at what could it matter, because you say, well, it does not matter if we adjust for all these different factors. Here's work of my colleague Ryan Muetzel, who actually in another talk on this section will go into much detail of this example. Here is just sort of to make you to a teaser, if you wish, of his work. And this shows the following. It shows the following, that what we did is we, in stepwise, we adjusted for different factors. Here, to be aware, it's not autism anymore. It's the relation between cortical thickness and attention. So we depict where essentially the thickness of children who have attention problems is thinner. And when we do a simple model, we get all these areas in red, these many, many areas. And then stepwise, we adjusted for parental education, income, prenatal exposure factors, maternal psychology, which are not in the typical neuroscience studies. And we show that with each of these additional confounding factors, essentially the areas which were thinner in those children with attention problems became less. So we essentially found that some regions completely disappeared, and this result would have been just attributable to confounding and nothing else. Okay, let's go to the second plague, the directionality, which I think is wonderfully illustrated in this much more recent picture. What is the directionality? Where are we going? What do I mean with directionality in imaging? It may not be clear to everybody. What do I mean with directionality of imaging? Well, essentially what I mean, is it brain or behavior? Or you could say brain or cognition, or is it cognition and brain? What is the direction of the association? And this is, again, work from my colleagues or from my group. in 2018 published in American Journal of Psychiatry, where we showed the following, where we were interested in, is behavior associated with MRI, or does MRI predict behavior changes? And we were lucky because we had a big group of children which we had assessed the behavior, and just a few months later, we assessed their MRI. And then 2 years down, the same group of children was measured both again behaviorally, and a repeated MRI was done. So that gives us an ideal scenario for answering the question, what is the direction of association? Here we depicted the schematic. We used the CBCL, that's a measure of child behavioral problems, which we related to MRI, correcting for the baseline. So it's essentially the change of MRI. And the same we do the other way around. We look at the brain morphology and we adjust it to behavior several years later, correcting for the baseline behavior and also the correlation at baseline. And that is a sort of cross-lag. We did it also with mixed models, looking at the association in both directions. The first thing I want to point out is that if we looked at subcortical structures, and you all know that's the summary of hippocampus, amygdala, and other structures, you can see that when we study that the correlation from the cortical structures at time 1 to the subcortical structures, subcortical structures at time 1 to subcortical structures at time 2 was 0.9. That means, and that's a group of 500 children, that means that there is essentially no change in the relationship. So those children that had a big subcortical structures had a big subcortical structures 2 years later relative to the other children. And that means we cannot study internalizing, externalizing, or any child behavioral problems in relation to the change of subcortical structures because there is not sufficient change. Is that clear? We cannot study that. However, when we looked at DTI, which is, you know, microstructure, white matter microstructure measure, we saw that that does change. So children who have the highest not need to have the highest FA values a few years later. And then we rated internalizing problems as a predictor of this change and white matter structure as a predictor of internalizing change. And what did we find? Well, these numbers give it away, but I'll explain it better on the next slide. What we show is that what I want to show is that the children who had high levels of internalizing problems at baseline, they grew less in their white matter, and those that had little problems grew faster. Or to say it in another word, it is essentially if you are anxious, if you are withdrawn, that's the internalizing problems. If you perhaps experience less environmental things, your white matter connectivity will grow less over time. But that means what we see is that the behavior precedes the brain change. So let's coming back to directionality. It means that we found that it is the behavior before the brain and not the brain that determines the behavioral change. So I'll go back a slide just to show it. It is this direction is much stronger. So anxiety predicts the change in white matter and not the white matter predicts the change in anxiety. So to summarize, the directionality is important, which essentially has one big implication that cross-sectional studies may be hard to interpret if it goes in both directions, because I'm not saying it's one direction or the other. I'm saying it's probably in both directions to some extent in different ages, which makes it very complicated. And this different ages is the next theme, the life course model. You all know that when change in the brain is the most prevalent or most drastic, when can developmental changes be expected? That is, I'll come to that in a minute, prenatally. And does that affect, do the results and how we interpret them thus depend on the age of the subject and on the brain changes? Just to show you very quickly, I'm struggling with my own work at the moment with surface area development at the end of pregnancy, so that it means that we have to study determinants of surface area change, mostly in a period plus minus a few weeks or months, perhaps if you wish, but really in a short period around the birth of the child, when the folding of the cortex occurs. Now, that's what we have to keep in mind. I'll show you examples of other work. Perhaps we start on the right side briefly to make this point. This is my work on the cerebellum changes in boys and girls. And you see that it starts when you go around the puberty ages, that it peaks the cerebellum growth and then it declines. So we find that there's growth and then there's decline. That has been shown from many structures by many people. So we know that gray matter peaks and declines around ages 10, 11. It depends a bit on what part of the brain you're in. But why is that important for epidemiological studies? It is so important because if you show that children with any condition have bigger brains, it could mean that they are advanced in the development, but it could also mean, if we are at a certain age, that they are delayed. So the interpretation of the directionality strongly depends on the age group. And actually, if you study children between the ages of 8 and 16, then you cannot, or very hardly, because there's a wide range in development, interpret the directionality. It's actually meaning we don't know if bigger is better anyway, but we certainly don't know that in these times of rapid development, because it essentially changes. So that's why it's so important. But it's also important at other time points, because we had shown in adults that the hippocampus predicts the incidence of depression. But then we went to the elderly and we found it was very different. In the elderly, there was no relation between the size of the hippocampus and incident depression, whereas the depression actually predicted the hippocampal decline. So even the directionality of the association can differ in different ages. That point is hopefully made, if you're still with me. Now let's come to perhaps what I would say the worst problem. I'm not sure it's the worst problem, but sometimes I perceive it at least as the worst problem. It is the multiple testing problem. And again, you could draw analogies with genetics, and you can also illustrate it, I think, with this figure. What I want to say is, if you go to the old epidemiological literature, essentially, people who are very famous epidemiologists argued that there are no adjustments needed for multiple comparisons. Things cluster and we have a good hypothesis and we need not worry. You can always argue we shouldn't bother. However, geneticists, once they studied not only 10,000 but 100,000 of different genetic variants, all of a sudden they realized we have to adjust for multiple testing. Otherwise, the nominal p-value, or in fact what we find as associations, can just be chance, and will largely be chance indeed. And I argue that in imaging, we are in the same era. We are in the era that multiple testing cannot be avoided, because any imaging will give you perhaps 300 areas, perhaps 500 variables. If you take the free surfer list, whatever you want to do, you get hundreds of variables. So I think an awareness of multiple testing problem is essential. It was the main problem in the candidate gene era, and I still think it is now the problem in the imaging era too. It is an increasing problem with multimodal analysis, everybody will tell you. So if we combine different imaging modalities. It is often conducted because let me continue with the next point. I'm not quite sure what I wanted to say here, actually. The different outcomes and different exposures in imaging are only moderately related. That's what I'm trying to say here, we are testing different hypotheses. If we test, let's say, the frontal lobe, the temporal lobe, the parietal lobe, then we are not studying the same hypotheses we are testing. And if we go to other structures like hippocampus, like amygdala, like different subcortical areas, we will test different structures. So I think we need to test correct for multiple testing. Now note that, and I can't go into detail, that we have shown that if you do the simulation models inherent in some of our software, that the multiple testing simulation models are wrong and they are too lenient. So we get away with mistakes essentially, or too high chance of type 2 error. And The other thing which I noted as a reviewer of some neuroimaging studies, it's a sort of tricky issue, is that if you control for confounding only at later stages of your modeling, then you can you do the discovery without very little confounders, and then later you control for confounders, then again you get the multiple testing problem. It's very subtle, but actually a very common mistake. And so I think we have to do multiple testing, though it's a big issue if we do want to do Bonferroni correction or false discoveries, which of these corrections to choose. So I'll just give very general advices. I think it doesn't work to say we have a very strict region of interest hypothesis. I think our hypotheses are often not solid enough, a bit dredged, reflect other problems. I think we should test multiple regions. I don't think we can focus just on one region of interest. So I don't think that is the solution that I sometimes see, that people say, I'll just look at the superior frontal lobe or whatever part of the brain. So I think we need to integrate effects across multiple measures into one model. So what we can do is like principal components, or we do factor analysis, or we do joint regions. So that's getting combined measures. And perhaps we need to move to more sophisticated analysis using machine learning or these type of approaches, or lasso regressions, where we can just control for multiple testing inherent in the procedure. I would like to talk a bit, very briefly, about one interest of mine, which I also think is a big theme in population neuroscience, and that's the specificity. I would like to talk about, this is the specificity. This is very specific now for child psychiatric problems, but I do think it's the same in adult psychiatry. I do think it's very similar in cognition and many problems that people here at Human Brain Mapping deal with. That is that the phenotypes we're studying are also closely related. And here's an example from adult psychiatry. It is an example showing that you will recognize some of these conduct disorder or inattention or social phobia or agoraphobia. All these different adult psychiatric traits are highly related. Depression, for example, has a correlation of 0.5 with conduct disorder, which depression and aggression seem so different, and yet they're all quite related. And you know that another way of looking at that, people with patients with autism high chances to also have ADHD. All these things go together. And many of you will be aware of the P factor. That's a sort of novel development where you see we will integrate in all these psychiatric traits into one factor, essentially showing a general psychiatric vulnerability. And I'll talk about that a bit. What we show here is a study of white matter microstructure in 3,000 children, where we looked at that's the DTA, the FA of the DTI values, the white matter microstructure of externalizing attention and internalizing problems. And to our disappointment, when we studied these children, we found no associations. So these traits in the general population were not associated with a clear pattern of white matter microstructure. So that's a negative finding. Some tendency for internalizing, but nothing much. And then we did the following. We defined a general factor. And we showed, and this is very specific, we showed, but I like the examples, I want to show it, what happens. We showed that if you essentially pool all these together in one general factor, you can show that the more psychiatric problems you have, the less white matter microstructure integrity you have. And that is very significant. So although these have no clear pattern, no association with white matter structure, if you pool them, you do find that. But what you also see that if you then correct for this general factor, and you look at the externalizing, but correct it for the general factor, you see another pattern is, it is a different direction. That is, more specific externalizing problems are associated with more white matter structure. And so in general, the problems show you less structure, But if you then just also for the externalizing, you see that. Why am I showing that? I'm showing that it is a very interesting pattern for me that associations in the brain really depend if you look at them very specifically or globally. If you just look at externalizing factors, you might not find one. But if you look at externalizing factors and correct for the general psychopathology factor, then you do see an association, albeit in a very different, unexpected direction. So it essentially means that if you have these combinations, if you look at depression, but you rule out cognitive declines, you might find very different patterns. If you have symptoms of autism, but you rule out ADHD, then you may find very different patterns. And that is a big dilemma. Do you want to do that or not? Both questions are valid, but they are very different. So co-occurring problems introduce heterogeneity. That's quite obvious. But co-occurring problems may explain our main effects. That is a challenge in much of psychiatry and cognitive phenomena too. You find very much the same in cognition. And so we cannot expect specificity. And to some extent, that is an artifact because in clinical practice, these things do go together. But we can, of course, in research, tease them apart or try to tease them apart. I'll go on with the sampling frame of the study base, or you could call it, do we want representativity? And the ideal sampling frame, so where do your patients, or in this case mostly, where do your population of imaging come from? Is a list. We want to know exactly the population where they come from, not just who turns up in our clinic, not just who wants to participate in our study, but no, we want to sample from a specific district, a specific area, specific city. And so ideally they would be then randomly sampled from that set of the population. Note that such a sampling need not be representative. So if you come from whatever city in the world, you can probably argue that if we sampled validly from that city, be it Seoul, be it Montreal, be it Rotterdam, where I come from, or be it Moscow, that this city, even if you have a study which really represents Moscow perfectly, is not representative of all the Russian population. So you can have a population based in your city, but it need not be representative. That is important. Importantly is much more to describe that in detail. But the question really is, do we need representativeness? And I think that's actually a mistake, but I'll illustrate that with the ABCD study. ABCD study is the biggest ongoing youth imaging cohort in the world. It's an American study. It's at 21 sites, and it's a fabulous, I think, a super study. But I do want to make one point, which I think they get wrong, if I may say so. They had a random selection of schools and sampled from these schools, but they essentially tried to get a representative population. So they approached the schools and said, we need a certain mix of ethnic and racial groups. We need a certain SES groups. So they were very restricted, and it's also very hard to get a good sampling of these schools. So essentially, at the end of the day, they had to go with whoever wanted to participate. And what they say themselves, they're very open about this, the information directs families to the research site by reducing any burden of school staff. Subsequently, interested families complete a brief telephone screening and, if eligible, are enrolled and scheduled. And with this procedure, what happens? What I would argue, it is well understood, and they say again themselves, that selection by families into the study with this self-selection is an unavoidable source of sampling bias. So what you see, what I want to point out is, this is interesting. Why is that interesting? Because if you sample from the, with this convenience sample, but you want to achieve representativeness, you may have a select group. Essentially what I'm trying to say, let me say it again to make it clear to the audience, otherwise sort of, what's more important? Let me put it this way. What is more important? That you have the group being represented, the ethnic distribution of the country, or that everybody has the same chance to participate and that the motivation to participate is similar, and that it's not biased. The people who are very keen to participate are very healthy, come from very organized families, are very happy to participate and have fun in your study, because then what am I trying to go at, is that you will have less people with, for example, psychiatric problems participating. And indeed, what we see in that study now is that the rates of problems are below that what you would expect. So it is not primarily about representativeness, but it is about the lack of bias. What we need at the same time, and that's very important to keep in mind, is that we need variation in exposures. So we want perhaps families who are disadvantaged, families who experience divorce, families who are unstructured, families, what others. We can also want positive experiences, perhaps people who are good in sports to participate. And we must make it easy for those who are busy with sport to also participate in our study. And that is not much about representativeness, but actually it's about generalizability. Are our results valid, and are they meaningful for other studies? And let me finish off with small sample sizes. That is another topic. And I think another problem, and Ioannidis' group, one of the critics of epidemiology and other studies, said why small sample sizes are so important is because they undermine the reliability of neuroscience. He argues that is the main problem. I think, as I told you, I think multiple testing is just as bad, but he argues we lack power. So here is a nice study, is how the effect sizes, so very small studies always find huge effects, which are then not replicable. But what I'm trying to say is most etiological effect sizes are small. I think it's an illusion to think that in neuroscience we deal with huge effects. We now know that genetic effects are small. I argue that in neuroscience effects are also small. We are in the business of understanding the brain, not in the business so much of understanding, but in the business of understanding causes of disease, prognosis, and these effect sizes are small. So we need big studies. We need big studies because effects are small, to address confounding, to address multiple testing, to address interaction, and to reduce chance finding. So the problems we have, many of which I touched upon, are worse in smaller studies. So it is very comforting to see that there's now a series of big studies ongoing which are addressing these problems, which are essentially forming population neuroscience. And with that, I'll leave you. Thank you very much for listening. I find this a very strange and awkward exercise to talk just on Zoom. I fear we have to get used to it. Thank you very much again. And if you don't believe in the New Testament 7 plagues, then you've got 10 plagues too, and then you can add, and you've probably got 20 plagues in neuroscience. We could talk about continuous straight categorical analyses, or that there's no open science, or the problem of p-value fixation. But I'll leave you with that. And again, thank you for listening.
So hello, everybody. My name is Christian Beckmann. I'm at the Dundas Institute in Nijmegen, and I wanted to talk to you about big data analytics for precision neuroscience today. It's a string of projects that we have been running at the Dundas Institute to rethink the way that we integrate population neuroimaging into analytical chains. And I wanted to report a bit on the challenges, but also on the advances that we've made in integrating population imaging into neuroscientific investigations. I like to start with this particular slide because it reminds me that with regards to understanding the brain, we are still somewhat like the 15th century explorers, haven't ventured out much yet. The reason why we got interested in this is that over the last decade or a bit more, we've seen a quite significant shift from small studies that typically involved 30 to maybe 100 participants via the Human Connectome project that involved already 1,200 participants, to now imaging epidemiological studies like UK Biobank, where in a few years' time, the full cohort of 100,000 participants will have their imaging data taken. And that naturally leads to the question, how do we leverage this big data analytics for precision neuroscience? Because it somewhat intuitively appears that it's not trivial to start making individualized predictions on the base of having access to 100,000 data sets. So in that context, it makes sense to think back to what we typically do. What we typically do in imaging neuroscience very much relates to normal null hypothesis testing, the scientific framework introduced by R.A. Fisher, who effectively says, well, we need to formulate a research hypothesis, and then we formulate the null hypothesis that predicts the opposite, and we're trying to refute the null hypothesis by finding evidence against it. So, classical example, there is no relationship between lung cancer and smoking. That will form our null hypothesis. And as soon as we find some evidence, we refute the null hypothesis. In imaging neuroscience, it typically boils down to estimating effect sizes across multiple subjects. And we start characterizing these different cohorts. Maybe in this example, for instance, it's 8 subjects that were measured twice during one session and the other, and we can characterize kind of the population variation during the session A and during the session B. And the null hypothesis is that there isn't a fundamental difference. The null hypothesis in this case is the effect difference in terms of the difference of means equals 0. And we then use something like a t-test to assess whether the null hypothesis is true. Now, when you think about kind of how the t-statistic works, it induces a particular type of thinking about the problem. So first, we start off by characterizing the two means we're interested in, x1 and x2. And that induces already the concept that both of these means are meaningful quantities. And we're going to return to kind of questioning that at a later stage of this talk. We then characterize the degree of variability, which we specify as some kind of sigma square, but also the sample size enters. In this case, it enters as square root of n. So what's the impact that that has with regards to our investigation? Well, the impact of that is that as n increases, even if the effect size difference stays the same, that same level of difference becomes more and more significant. Well, conversely, it also means that as n increases, we can start detecting smaller and smaller differences between the two different cohorts, to the point where, in terms of explained amount of variance, that difference becomes relatively useless, in that at the large cohort level, it has a p smaller than 0.05 maybe, but it does not allow us to make meaningful predictions about an individual sample from either the blue or the red cohort in this example. So this is what we are trying to overcome using tools and techniques that are more sensitive, more specific, and biologically interpretable at n equals 1. So the talk I've structured in 3 ways. It's largely going to concern analytical techniques that I want to describe. And it's largely based on this kind of, or motivated by this quote from Sidney Bremer, the Nobel Prize winner in physiology and medicine, who says progress in science depends on new techniques, new discoveries, and new ideas, probably in that order. So in the first instance, I'm going to talk about big data for systems connectomics. So how, with high N, we can start learn about systems in terms of moving away from simple statistical characterizations towards understanding how systems interact, maybe even understand hierarchical organization in systems. I'm then going to argue that in order to actually make big data work for precision neuroscience, we need biological interpretability at n equals 1. And I'm going to introduce a particular approach to resting fMRI in this case that we call connect-topic mapping, that we think is a good candidate for delivering something that is interpretable at n=1. And I'm then going to describe how these endpoints that become meaningful at n=1 can be used within a framework which we call normative modeling, that uses a characterization of cohort heterogeneity to deliver precisely what I was talking about before, which is precision neuroscience in the sense of I can take an individual measurement and compare it to the range of variation I see at the cohort level. So let's start with the first part of the talk, big data for systems connectomics. In order to obtain big data, clearly we need some kind of measurement that is homogeneous in the sense that maybe it can be taken at multiple sites quite easily. Maybe it can be taken in different cohorts with relative ease. And resting fMRI has established itself somewhat as a go-to method from the imaging perspective with regards to this kind of easy applicability. We can apply resting fMRI in child and adolescent cohorts, in neonates, in individuals with heavy levels of dementia. Relative to task fMRI, it is a comparatively easy functional modality to apply across a wide variety of individuals and across a wide variety of image acquisition equipment. Many of the things I'm going to talk about later on, however, will be universal in the sense that you can fit in whatever kind of measurement you're taking, as long as it is a quantitative description of underlying biology. So for instance, it can also apply to diffusion data. But how is high-N useful to test actual models of function? Well, many of the models of function that we've encountered, in this example, for instance, the very iconic one of the connectivity within a particular system or system of importance, derive from high cohort data. So in this example, for instance, the COCOMAC data, the macaque macro connectivity data, together with other information that was available at the time, has led to this iconic wiring diagram of the visual system that was first published in 1991 by Fellerman and Van Essen. So that allows us to conceptualize human brain function in this iconic way. Malcolm Young at Oxford a year later then used multidimensional scaling to take this same matrix, the COCOMAC matrix, and characterize the organization that is obtained within that matrix in terms of a dorsal and a ventral stream. So that forms one of the very few almost truisms in imaging neuroscience that is even taught at the level of a master neuroscience course. So one example where high numbers of individuals, big data, functional data is useful is that we can basically start to revisit these very iconic ways of looking at the visual system and now make that specific to humans and make that specific to brain function. The COCOMAC database is anterograde and retrograde tracing data in the macaque monkey. So it describes structural connectivity by and large in a different species. But with something like the Human Connectome project, where we have 1,200 individuals and we have resting fMRI functional observations in these individuals, we can actually come up with a similar matrix. In this case, we've taken an atlas of the visual system, Sabine Kastner's atlas from Princeton, where there's a characterization in terms of 50 different regions. We can calculate the region by region partial correlation of the functional observations taken. And we can subject that matrix, just like Malcolm Young has done about 2 decades ago, about 3 decades ago, to multidimensional scaling to, in this case, start characterizing the functional interaction within these 50 areas in terms of a wiring diagram. So we've done that a few years ago, and lo and behold, what we find is that in the human species, we don't see just a ventral and a dorsal stream. We actually best characterize the organization, the functional organization, in terms of 3 putative streams: a dorsal stream, a ventral stream, and a more lateral stream. So a second aspect of high N in this particular case, some of you will know that the human connectome data actually has 1,200 subjects with resting fMRI recorded across 2 different days, across multiple sessions. So we have a day 1 and a day 2 estimate. So high N can actually become useful in the context of delivering test-retest results. So for instance, in the human connectome data, we can look at what happens at in the day 1 data and in the day 2 data. And we can start characterizing the within stream versus the between stream partial correlation, the Z-transform partial correlation scores. And we find extreme high replication in that sample. So again, with high N, we can split the cohorts into subsections that are used for discovery and another subsection that is used for replication. We can even go beyond. So this is an example where resting fMRI in a high N in a big data cohort was used to verify or test a particular hypothesis that already exists in the neuroscience domain. We can also go beyond and actually start looking at the data to suggest hypotheses. So for instance, in this example, we've used the same data source, the human connectome data, in this case, 876 subjects, to look again at the partial correlation across the visual connectome on the left, but now characterized in terms of the heritability. So in this particular example, the human connectome data contains 1,200 subjects, and these are organized in terms of 300 families with 1 twin pair and 2 non-twin siblings per family. So we can start estimating the degree to which the partial correlation of functional connectivity is heritable. And what that allows us to do is actually characterize the heritability across the hierarchy of processing. So what you see on the right-hand side is a hierarchical level away from V1, the primary entry points into the visual system. And what you see is that different areas with different distances away from V1 exhibit different levels of heritability. The reason why we found this to be very interesting is because heritability can somewhat be seen, given that it's basically talking about how genetically determined a certain phenotype is, can be seen as providing a limit on plasticity. Plasticity being the ability to flexibly adapt function. And clearly, whatever is heritable can no longer be adapted. So they basically complement each other. And characterizing the entire hierarchy of visual processing in this particular fashion, we can start testing hypotheses now about how plasticity develops as a function of hierarchical level. So in this particular case, for instance, we started speculating that there is 2 different components of plasticity that are going on. There is some kind of short-term plasticity, which you all experience when you walk from a very bright room into a very dark room. Your system adapts very quickly, the visual system, and that will happen very early on. But there also is long-term plasticity, and long-term plasticity refers to real kind of changes in the organization that will probably take much, much longer timescales. And because it takes more timescales and more fundamentally changes the way that regions interact with each other, is subject to what people have called the coding catastrophe, which refers to the fact that if you're changing the interaction very early on in a hierarchical system that has top-down and bottom-up modulation, if we were to change, for instance, the way that V2 interprets the input from V1, then all the stages after V2 would have to update their code. Whereas if you only change at the very high level of the hierarchy, right, only very few further on processing levels would need to change their code. So that seems to be kind of a more economical way of introducing plasticity. But based on this speculation, we'd actually assume that there is some kind of short-term plasticity that decreases as the hierarchical level increase, and another component in terms of long-term plasticity that increases. And indeed, that's precisely what we see in the data. So the two combine to give you some combined kind of level of plasticity that fits the data very well. So this is an example of how, using big data resources, we can actually start talking about biological change over and above just simple statistical assessments. Now, the second thing that I wanted to talk about is how important it is to remain specific at the phenotypic level, so phenotypes at n equals 1. And I'm doing that by introducing connect-topic mapping as a way to introduce topographic organization as a critical feature in biological information processing. What I mean by that is, when you look at functional connectivity, we know already that within a given area, for instance, a sensory motor strip, as you move from the medial wall to the lateral wall, peak functional connectivity in the opposing hemisphere also moves from the medial wall to the lateral wall. So there is fine-grained organization, topographic organization, functional variation within areas that we would consider functionally to be relatively homogeneous. What we know over and above this, however, is that particularly we know this from primary sensory modalities, is that there is functional multiplicity. So as an example, I can probe the entire visual system in terms of fovea versus high eccentricity, and I can probe it in terms of rotating bars. And what we then observe very robustly across multiple studies is that, again, we have multiple modes of functional organization that coexist simultaneously. And now, putting that in relation to what you also hear at this educational session, if you actually use the wrong models, you can start detecting things with high reproducibility and high replicability, but without biological reality. So in the presence of gradients, for instance, if there is a gradual variation, you will get spurious clusters, and you will get these spurious clusters with high reproducibility and replicability. If I have a gradient of organization like here with the dots, and if I enforce a parcellation in terms of two parcels, I will get two parcels, and I would get that again and again and again. Likewise, if I take two gradients and they overlap, I will see an ensuing gradient that doesn't have any biological reality. It does not map onto the first or the second, but I will see this kind of clustering again and again and again. So biological interpretability needs to be at the heart of anything that tries to move from big data to individualized predictions. What we've been working on is a tool that we call connectivity gradients, congrats, connect topic mapping, that will allow us to estimate these gradients. And we've combined that with a particular technique from geostatistics called trend surface modeling, And what trend surface modeling allows us is to characterize these surfaces, these gradients, in very, very few parameters and actually do statistics across them. We can show that these things are very robust. We have very low root mean square error, even with normal data. In this case, in the white dots, you see what happens if you downsample the HCP data to more like 3-second DR. So these gradients become stationary after maybe 10 minutes. And indeed, we can start estimating the things that we know about in, for instance, simple processing areas like the visual system. So we can take an individual subject and probe for eccentricity and polar angle, and we get certain organization. And if we apply connectopic mapping, we see similar organization at n equals 1 from the resting data. Now, this now allows us to start mapping entire systems. So in this example, for instance, we're mapping that into the striatum. The motivation for that is the iconic work from Susan Haber and Brian Knudsen, where they use a meta-analysis of monkey data to speculate about there being a ventral to dorsal gradient in the striatum and different areas of the striatum mapping differentially into frontal and prefrontal cortex. So using these tools and techniques, we now have endpoints that work at n equals 1 and allow us to characterize this particular brain area in terms of its connectivity with the rest of the brain at n equals 1 in vivo from resting fMRI observations. And using the trend surface modeling, we can actually start looking at how similar these effects are across individuals or across sessions. In this example, we're using what's called mate matching retrieval. So we have 60 subjects scanned twice, day 1 and day 2. We can estimate the gradient. Some of them show an artifact clearly. But if we were to pick any gradient from the first day and try to look at how often does it map onto the its own gradient from the second day, chance level would be at 1/60, so about 1.6%. With these gradients, we're getting around 60%. So that clearly means that while there is very high levels of commonality between subjects and between sessions, there also is inter-individual differences that can be exploited. And one example of exploiting those inter-individual differences is to map it onto other data from the same participants. So for instance, in this example, we are mapping that to the demographic and cognitive measurements, behavioral measurements in the HCP. So we can look at the gradient, we can simplify the gradient using trend surface modeling into 9 parameters. And if we map these parameters into the cognitive behavioral battery of the HCP, we can characterize how different types of behavior, how different behavioral domains appear to correlate with inter-individual variations at the n equals 1 level of these gradients. So we can see, for instance, that the striatal organization of connectivity maps most strongly onto psychological well-being, onto the rational fMRI task, and onto delay discounting. So the third aspect that I wanted to talk about is normative modeling. So how can we bring these things together now that we have endpoints that are meaningful at n equals 1? How does that help us in moving from big data to making individualized predictions? So the classical approach I was talking about at the very beginning, the 2-group kind of approach, uses high N only to gain statistical power. And in doing so, we estimate smaller and smaller effects and get to the point where we get poor individualized predictions because we no longer explain variance. The normative approach tries to understand heterogeneity through large cohorts. So it's moving away from only characterizing a difference in mean, so the mean is a first order statistic, to characterizing heterogeneity, so higher order statistics through large cohorts. And if we get that right, we can start quantifying deviations of an individual participant relative to that normative mean. Just to hone down that idea, what we do in a classical case control comparison, when we only have two groups and we're looking for a difference in means, so we kind of assume that both controls and cases are valid categories. But in many clinical investigations, we know this not to be the truth. We know, for instance, that in many disorders, there likely is subgroups that have very different expression of clinical symptoms. Or if you think in terms of autism, for instance, we can think of disorders or alterations or neurotypicality in terms of a spectrum of function, right? Where those individuals that we would term cases end up being at just a different place on that spectrum. Or indeed, it could be a mixture of all of these things. Now, the classical case control comparison, the classical way of categorizing one group versus the other using a simple t-test, for instance, only really applies to the very first top left way of seeing our clinical world. What we're doing instead with normative modeling is we take some inspiration from what is being done if you take a child to a pediatrician. In that case, that child at n equals 1 is being mapped in terms of its height and in terms of its weight against these normative charts that have been estimated across large cohorts. So these growth chart approaches map age in months to weight, for instance, in kilograms. And we have associated confidence intervals that will look at how much is their normal variation within the normal cohort. And we can apply exactly the same principles to imaging data. So for instance, we can map reward sensitivity against brain activity. All we need for that is high-end that will allow us to actually map any kind of clinical or behavioral predictor variable against quantitative biological variables. Connectivity from resting fMRI, activity from task fMRI, cortical thickness from estimating kind of cortical thickness via software like FreeSurfer, for instance, right? And if we do so, we can start actually characterizing the normative range of these quantitative biological measurements. And similarly to before, get centiles of variations that encode our belief in the normal level of heterogeneity within that sample. So these centiles map onto predicted brain activity for any value of covariates, and we can do this in high-dimensional spaces to look at multiple covariates simultaneously. And the beauty of this approach is that if we happen to have a new measurement, we can characterize that new measurement both in terms of how much uncertainty we have, but also what is the predicted error, i.e. what's the deviation from the predicted mean at that level of clinical covariate. So if this is, for instance, activity pattern in fMRI, we can start building up these normative models for every single voxel. We can estimate deviations for all voxels or vertices, and we can derive normative probability maps. And beyond that, we can even start kind of defining things like subject level deviation indices, where we can use things like extreme value statistics to come up with individualized predictions of, is this subject deviating? So we can look at kind of a summary statistics of deviation, but we can also look vertex or voxel specific using thresholding approaches, for instance, on these normative probability maps to define where and how an individual ends up being different from the normative cohort. Now let's go back to the striatal functioning to see how that works in practice. I've already shown you kind of these connectivity gradients in the striatum and how in the HCP that maps onto normal behavior. But we can also model kind of that normal behavior in terms of abnormal associations in individuals. So we can, for instance, look at the 30 highest alcohol users and map the number of alcoholic drinks per day against these trend surface parameters. And what we find on the left, you'll see that association, extreme significant correlation only within those 30 highest alcohol users with regards to some of the trend surface parameters that describe the organization of resting fMRI in this writing. Similarly for smoking, similarly for the number of depressive symptoms or episodes. All of this is from the HCP data, so these are technically healthy control subjects. We can also do that in a clinical cohort. So for instance, we are looking here at the association between UPDRS symptom severity score and trend surface parameters. And we can actually identify an entire trajectory of change. So we can look at these associations, say, well, if we take these 4 particular subjects that lie really nicely near to the regression line, we can start looking at what happens with the imaging phenotype as our UPDRS symptoms severity score increases. So we can reconstruct, using the trend surface parameters, the phenotype that we're interested in and see what happens phenotypically. What happens in a patient that is more heavily impacted by Parkinson's disease than someone who has a much lower UPDRS symptom severity score. So the way that we conceptualize this, how do we leverage big data analytics for precision neuroscience, is to benefit from our ability in large samples to better characterize the variation across population. So that's a bit of a fundamental shift in that we no longer exploit high N in terms of identifying kind of smaller and smaller differences in the mean, in the first order statistics, but instead we want to capitalize on the ability to estimate heterogeneity in the sample better and better as N increases. That only works, nevertheless, if we still have phenotypes that are meaningful at N equals 1, interpretable at N equals 1. In this case, I've been pitching the connectopic mapping quite a bit. Right? But what this normative modeling allows us to do is to accurately quantify uncertainty and then make predictions at the level of an individual subject. And in doing so, particularly for the clinical neuroimaging domain, it has massive advantages in that it removes the need to artificially dichotomize experimental groups in terms of talking about patients and controls. There no longer is an average patient like there is when you actually just calculate the difference in means between two groups. And instead, it starts viewing pathology as a departure from the normal model. So I look forward to many interesting questions. And I thank you for your attention. And I thank all of these many members of my group, both at the Dundas Institute in Nijmegen and the collaborators at the University of Oxford, who have contributed to this work. So thank you very much.
Thank you for joining us today. My name is Anqi from National University of Singapore. Today, I'm very happy to share with you some of our research work on population neuroimaging meets genetics, important considerations and possible solutions with data, both big and small. Recent growing population neuroimaging study allow us to investigate massive association between brain imaging measures and health outcomes. And such association can provide insights of brain development and aging in link with physical health, blood acids, lifestyles, such as the one shown in the UK biobank study. Given the large dataset, there is also a great opportunity for us to investigate genetic markers associated with brain imaging phenotypes, and hence to understand biological mechanisms that are related to brain structure and function. In this talk, I will discuss how to examine association of genetic data and brain phenotypes when the sample size and data dimensionality are large. What are the challenges and possible solutions? In addition, when the sample size is small, but the dimensionality of the genetic data is large, what are the challenges and solutions? I will introduce several solutions to deal with genetic data, such as haplotype analysis, polygenic risk scores, and gene site analysis. Finally, I will touch on gene expression from postmortem brain in relation with brain imaging phenotypes. Genome-wide association is the most popular approach to examine the relationship between genetic variants and brain imaging phenotypes. Here, the brain imaging phenotypes can be scalar measures, such as the structural volume, or voxel-wise imaging phenotypes. Currently, the workhorse tools of GWAS on neuroimaging are mass univariate, where a regression model is fit separately at each imaging measure. In this regression, brain imaging data is considered as a dependent variable Y, and genetic variant is considered as an independent variable, and there's a set of demographic data, such as gender, age, and education, and these variables are considered as confounding variables. And regression model will be able to model the link between the Y brain imaging measure and the genetic variants. And this analysis has to be repeated for every pair of brain and genetic measures. Here shows the Manhattan plot. And this Manhattan plot shows the significance level of association between the individual SNPs and the putamen volume. There are only few SNPs whose genetic variants are highly associated with putamen volumes. When dealing with voxel-wise imaging measures, we need a massive statistical test. Hence, a statistical approach to deal with correction for large number of statistical testing are needed. In addition to that, big data also have bigger confounding troubles. What is a big confound trouble? In this regression model, we assume we have included a complete set of confounding variables. Hence, this residual estimation is proper, and such as we have a proper statistics for the coefficients that related to the relationship between the genetic variants and the brain imaging data. However, in reality, and the selection of X is based on our prior knowledge, or sometimes we may not even measure the complete set of confounding variables in our experiments. And in this situation, and the residuals could be inflated, and such as the statistical results for beta down here, it could be deflated as well. So in such case, and the conclusions from this linear regression can make our hypothesis tests conservative. And sometimes the missing covariates Z down here, it can be correlated with the genetic variable we are interested in. And in this situation, our statistical findings could be positive or negative bias for the association between M and Y. The one way to solve this problem is to reformulate our regression model by inserting missing confounding variables Z down here. Where X here is no confounding variables such as gender, age, education, and based on our prior knowledge. And down here is genetic variants we are interested in. And Z here is missing confounding variables we're going to estimate from this regression model. And beta Z is also an unknown coefficient that indicates the relationship between the missing confounding variables with imaging measures we're going to study down here. So there are many ways to solve this problem. where partially the model is known and partially the model is unknown. So we have proposed one of the ways to solve this problem in this paper, and software is actually available in this website. You can download it. Let me give an example to illustrate the importance of estimating missing confounding variables in GWAS study. Here, we are particularly interested in epigenetic markers. We are looking at how our body remembers what happens to us previously, and how does that affect brain development. For each of the units in this study has both diffusion tensor imaging data as well as methylation lossing. We consider fractional anisotropy measures at each voxel as y in this linear regression, and each methylation markers is considered n, and confounding variables we know includes gestational age at MR scanning time, gender, as well as the birth weight of units. And Z down here is missing covariates, missing confounding variables we need to estimate. And this regression model has to run for every voxel in the brain as well as every methylation markers. So the correction for multiple comparison was done across the whole brain as well as across all methylation markers. What we found is that these particular CpG markers that are near to the gene MOC2 is actually associated with the FA values in the thalamus region. And the thalamus region is particular, has a high concentration of calcium. During the estimation, we found the two missing confounding variables across the entire neonatal brain. And these two confounding variables are actually highly correlated with a neonatal birth length as well as a total brain volume. So in our study design, we never sought birth length and total brain volume that could influence the association between the epigenetic markers as well as the neonatal diffusion measures. And this is to point out the importance of estimating these missing covariates, and such as that will be able to increase the statistical power in the association study between epigenetic markers as well as the brain imaging data. Beyond the confounding problems, there are other challenges in GWAS study. For instance, common genetic variants only account for a small fraction of the heterogeneity of brain phenotypes. To give an example, this COMT WOW158 match SNP. It's a very popular SNP that people often study. The reason because the COMT regulates dopamine signaling in the prefrontal cortex. And this particular SNP leads to amino acid change from valine to methionine at position 158. The WOW allele is suggested as a predominant factor that determines higher COMT activity in prefrontal cortex, which presumably leads to lower synaptic dopamine levels through enhanced degradation. This particular SNP indeed modulates the association of antenatal maternal anxiety and the sickness of inferior frontal cortex. But there are other SNPs in the COMT genes, and sequence variants lying in the other loci within the COMT genes also affect the gene function, ultimately resulting in altered enzyme activity and adding a complexity to the functional as well as clinical implication of COMT variation. To further examine additional two COMT SNPs, and here we show these two SNPs also modulate association of antenatal maternal anxiety and cortical sickness of superior frontal cortex as well as parietal cortex. Certainly, we can repeat the analysis to every SNPs on the COMT genes. Nevertheless, the genes normally have a nice block structure called the haplotype block. Within each block, the genetic variants of these SNPs are highly correlated with each other. In other words, the genetic variants of one of SNP can represent the genetic variants of this entire block. For COMT genes, there are 3 independent blocks. And using these 3 blocks, we can form a haplotype for this particular COMT genes. And this approach allows us to reduce the number of statistical analysis we need to do in order to examine the entire COMT genes, but in the meantime, it increases statistical power. For instance, using the same data, if we look at the haplotype, and this haplotype actually modulates the association of antenatal maternal anxiety with the cortical thickness of inferior frontal cortex we see before, and superior parietal cortex, as well as superior frontal cortex. So you can see the regions involved is much larger than what we see before when using individual SNPs. But in addition, statistical power in terms of p-values is much stronger. What we learn from the haplotype analysis is that considering the gene information as a whole, rather than individual SNPs, can improve statistical power. In other words, accumulative effects from individual SNPs can improve the detection on the heritability of brain imaging phenotypes. The second approach we will introduce is called polygenic risk score. We will give an example to illustrate how to compute the polygenic risk score for individual subjects. In particular, in this particular example, we investigate how genes and antenatal maternal depression affects fetal brain development. The dataset includes neonatal brain images as well as genotype data. The risk alleles and effect size of SNPs are established from existing genome-wide association study for depression, using relevant discovery samples based on their p-values below a defined threshold. Polygenic risk score is calculated for individuals in our sample as the sum of the count of risk alleles weighted by the effect size in the discovery sample. Previous study showed the polygenic risk score for major depressive disorder predicts the risk for depression and modulates the influences of childhood maltreatment on depressive symptoms. Our study also showed significant interaction between antenatal maternal depressive symptoms and neonatal polygenic risk scores on the right amygdala volume. Neonates with high polygenic risk score and born to mother with higher depressive symptoms show a larger amygdala volume. We employ gene network analysis and identify biological pathways that can potentially contribute to such an interaction. The genes that form a glutamate receptor activity most interacts with maternal depressive symptoms on the neonatal right amygdala volume. Postmortem studies with major depressive disorder suggest altered glutamate synaptic signaling is a treatment for major depressive disorder. The antidepressant blocks stress-induced increase in glutamate release in the amygdala and modulates a behavioral response to stress. This example illustrates the use of polygenic risk score in imaging genetic study and its potential statistical power to detect polygenic effects on brain imaging phenotypes. So far, I only introduced a few solutions to the first challenge that is related to our common genetic variants. Beyond the common genetic variants, we know rare variants account for missing, perhaps hidden heterogeneity, which is not even considered in GWAS due to a lack of statistical power. Rare variants can only be identified using GWAS when sample size is extremely large, which is difficult to achieve in imaging genetics. Is there any possibility to study rare variants effects on the brain, given the current the sample size we have? There are some ways to do it, and for instance, we can consider gene as gene sites. And regardless of what SNPs is inside, whether it's a common variant or the rare variants, we're going to all include into this gene sites. We can formulate the effects of genes interaction with environmental measures, for instance, in the following way. And here we have gene size information, and E down here is environmental factors we have down here. And in order to look at the interaction between the two, we have the interaction terms down here, where E is environmental factor and G is gene size. W here is the weight measures for individual SNPs, and you can think of, and this can be adopted from the GWAS study, or maybe this is just related to the relationship between the SNPs down here. And these two measures actually can generate genetic scores that will be able to interact with environmental factor. And pi down here is the coefficient that related to how strong the interaction between the two contributes to the brain imaging phenotypes right down here. And we also introduce random effects. For instance, if individual SNPs has a different effects to the outcome measures, and the delta down here will be able to model these heterogeneous effects from individual SNPs in the gene sites. And this approach allows us to be able to combine the rare variants into the gene size, regardless of what the sample size we have. To give an example, and here we are interested in looking at the FTBP5, particular genes that regulate HPA access. We are looking at its modulation to the relationship between maternal depression and neonatal hippocampus. The data sets we have is 161 mother offspring diets, brain imaging data, as well as genotype data. If you look at individual SNPs in these particular genes, and some of the genes, some of the SNPs actually have a positive association with outcome measures, and some have a negative association with outcome measures. And certainly this is a heterogeneity of the effects from individual SNPs in these particular genes. And this model we just introduced are able to model such heterogeneous effects through this random effect factor. In the meantime, we also be able to look at homogeneous effects from individual SNPs that contributes to the outcome measures. And we look at that here. What we found is that for the neonates with a higher genetic risk, and if the maternal depression symptoms is high, the hippocampus volume is actually larger. And this is consistent with what we just showed in the previous slides, that the right middle volume is actually associated with larger maternal depressive symptoms. So this actually gives us quite big strong statistical power to look at the gene as a set of genes together in order to boost up the statistical power. You may ask how to choose a gene set if I don't have a specific hypothesis. We all know gene is expressed in specific brain region at specific timing. If we know the brain regions we are interested in at a particular lifetime, we should be able to use the gene expression information to locate which are the genes that are most interesting in this particular region and particular time. In the next few minutes, before I end my talk, I will discuss that the neurotranscription information is actually highly correlates with variation of cortical morphology. Such correlation actually can reflect the biological process related to brain development. Here we extract the gene expression information from a brain span database, and we'll be able to actually measure the gene expression information at specific brain region from fetal stage to early childhood. So we then have brain imaging measures, including structural MRI as well as diffusion imaging data from neonatal to early childhood. So here we show the cortical thickness was associated with a glial dendrocyte gene expression during trimester 1, and the actual site expression during trimester 1 and 2, and fractional anisotropy measures was associated with gene expression in the microglial cells, particularly in trimester 2. So we then take top 10% of genes whose expression are highly correlated with cortical measures. We basically looking at their biological processes that contributes by these genes. And this biological process is particularly involving cell migration, cell proliferation, as well as vascular development. And those information are particularly happening during the fetal stage. In addition to that, we also looking at, and here we show that the gene expression information in neurons as well as in actual sites is highly correlated with cortical thickness data in 4 years, 6 years, and 7 years. And similarly, we see FA values as well as radio diffusivity measures highly correlated with gene expression information in neuron and actual sites, particularly in 4 years and 6 years. Again, the top 10% of genes from this high correlation analysis, and that basically contributes to the synapse signaling information in early childhood. To summarize, to investigate the relationship between gene expression information as well as the morphology, we are able to identify biological processes that are related to brain development. And this is very similar to what we have discovered in the postmortem analysis. To summarize what we have discussed today, so I basically talk about some of the challenges related to confounding variables. The sample size is small. How we deal with common genetic and rare genetic variants in the imaging genetics study. We introduce a couple of solutions that allow us to estimate the confounding effects. In addition, we also introduce a polygenic risk score, haplotype, as well as gene set analysis to study common as well as rare variants together. Finally, we discuss gene expression information is very important for us to look into it. And since the gene expression information encodes both spatial as well as temporal information of the brain. And using this approach that allow us to pinpoint when when gene is functional in which location in the brain, so that allow us to be able to study gene in relation with brain phenotypes in a better manner. Finally, thank my lab members who have been contributing to the work I discussed today, and thank you for your attention.